Welcome to Cosmos Explorer. I'm Dr. Eugene. Today, we're diving into a breakthrough discovery, the first ever X-ray image of the invisible bubble surrounding a sun-like star. NASA's Chandra X-ray Observatory has captured the first ever X-ray image of an astrosphere surrounding a young, 100 million-year-old star located 120 light-years from Earth. This result will be published in the Astrophysical Journal. The universe is home to countless stars, and around them, there are likely even more planets. Among these worlds, some may have liquid water and may even be able to support life. However, whether a habitable environment can be maintained depends strongly on the activity of the central star. Stars do more than shine. Their surfaces are sites of intense activity, releasing both light and streams of charged particles. This flow of particles is known as the stellar wind. As the stellar wind expands into the surrounding space, it pushes away interstellar gas and dust. This process carves out a vast region around the star like a giant bubble. These invisible bubbles created by stellar winds are called astrospheres. In simple terms, an astrosphere is the region around a star shaped by its wind. This region acts as a shield, reducing the impact of high-energy particles from deep space and helping shape the environment of the surrounding planets. That is why understanding astrospheres is important when we think about planetary evolution and the conditions needed for life. A similar bubble also surrounds our own sun. The astrosphere created by the sun is specifically called the heliosphere. Formed by the solar wind and the sun's magnetic field, it acts like a huge protective barrier surrounding the entire solar system. It helps reduce the impact of some galactic cosmic rays produced in violent environments, such as supernova explosions, helping keep the solar system, including Earth, in a relatively stable environment. We have already confirmed the boundary of this heliosphere through direct exploration. In 1977, NASA launched two legendary spacecraft, Voyager 1 and Voyager 2. They continued their journey far beyond the planets and eventually crossed the boundary of the heliosphere. After a journey of more than 35 years, Voyager 1 reached interstellar space in 2012, followed by Voyager 2 in 2018. The Voyagers physically left the sun's bubble and sent back direct data about the environment outside it. Thanks to studies of the heliosphere, we now know that these invisible bubbles are not just theoretical predictions, but real, three-dimensional structures that change over time. Recently, a research team led by Dr. Lisse of Johns Hopkins University carried out detailed observations of a young, solar-type star called HD 61005, located about 120 light-years away. They successfully identified the astrosphere around this G-type main sequence star through X-ray imaging for the first time. This discovery offers new clues about what kind of stellar wind our sun may have produced and what kind of bubble it may have created when it was young. Although HD 61005 has a mass and surface temperature similar to those of the sun, it is only about 100 million years old, far younger than the present-day sun. It is classified as a G8.5V main sequence star and is often treated as a stand-in for the young sun. This star is also known to be highly active. In X-rays, it is brighter than the present-day sun, and its stellar wind is thought to be stronger and likely faster and denser than today's solar wind. These conditions make it easier to observe the region where the outflow collides with the surrounding medium and forms an astrosphere. It was already known that a large amount of dust surrounds HD 61005. By combining visible light images from the Hubble Space Telescope with millimeter-wave images from ALMA, we can see a thin, dense dust disk around the star. Outside this disk, fine dust structures stretch backward like wings. Because of this unusual appearance, HD 61005 is nicknamed the Moth. These wing-like structures are considered clear evidence that the dust around the star is being strongly affected by the surrounding interstellar medium. There is also evidence that the interstellar environment around this star is much denser than the one around our solar system. The density of neutral hydrogen may be as high as 100 atoms per cubic centimeter. That is about 1,000 times higher than the typical value of about 0.1 near the Sun. In such a dense environment, the collision between the stellar wind and the surrounding matter becomes much stronger, making this system an ideal target for identifying an astrosphere. To investigate this, the team carried out X-ray observations with the Chandra satellite. Here is what the actual data looks like. On the left is the dust distribution seen by Hubble and ALMA. On the right is the X-ray distribution captured by Chandra. In the X-ray image, we see a roughly circular glow. However, from the X-ray image alone, it is difficult to tell whether this glow is simply the star's corona blurred by the telescope, or a separate component coming from the surrounding region. To address this, the research team overlaid the X-ray distribution on the Hubble image. The white features come from Hubble, while the red and blue colors show the X-rays. In this composite image, we can see that the X-rays do not extend sideways along the flat dust disk. Instead, they form a circular glow centered on the star. The X-ray emission reaches the base of the moth's wings, but its shape is clearly different from the dust structure. If the X-rays were coming from the dust disk itself, they would share the same flat, elongated shape. Instead, they show a rounded expansion around the star, separate from the dust. This difference in shape provided strong evidence that the X-rays come not from the dust disk, but from the astrosphere expanding outward. To confirm the nature of these X-rays, the team analyzed the X-ray spectra from the inner and outer regions of the system. This is the actual spectrum. The horizontal axis shows X-ray energy, and the vertical axis shows brightness. The left panel shows the raw brightness of each component. The right panel rescales the brightness so that the shapes of the spectra in the inner and outer regions can be compared more easily. The blue data represents the central region, including the star itself. This is consistent with emission from the hot corona on the star's surface. However, the red data from the outer region shows features that are clearly different from those of the center. In particular, strong emission lines from oxygen and neon were detected. This is evidence for a process called charge exchange. Put simply, charge exchange is a process in which ions capture electrons from neutral atoms. When highly charged ions in the stellar wind collide with neutral gas around the star, they can capture electrons from that gas. As those electrons settle into lower energy states, they emit X-rays at specific energies, producing bright emission lines. This same process is also seen around Earth, where the solar wind interacts with the outermost layers of our atmosphere. That is why the oxygen and neon lines provide strong evidence for a region where the stellar wind is colliding with interstellar matter and exchanging electrons. By analyzing both the shape of the emission and the composition of the light, the team showed that a high-speed stellar wind is crashing into dense interstellar gas, roughly 100 astronomical units from the star. In other words, the circular X-ray glow captured by Chandra is the astrosphere surrounding the star. So, how does this compare with our own solar system? This diagram compares how gas and dust interact with the bubbles surrounding the Sun and the HD 61005 system. On the left is our solar system. The outermost boundary of the Sun's bubble is labeled the heliopause. Inside that is the termination shock, where the solar wind begins to slow down from supersonic speeds. In our solar system, the heliopause is about 120 astronomical units from the Sun, and the termination shock is about 90 astronomical units away. On the right, HD 61005 appears to have a similar overall structure, but with one major difference: orientation. In the solar system, the surrounding gas and dust flow in almost parallel to the orbital plane of the planets. However, in HD 61005, the gas and dust appear to strike the disk almost from directly above. The research team believes this frontal impact distorts the bubble and helps create the unique wing-like structure of the moth. This discovery is a major step forward, providing the first direct evidence of how protective bubbles around planetary systems can form through collisions between stellar winds and interstellar matter. The shape and density of these invisible bubbles can help shield planets from dangerous radiation coming from deep space, and can strongly affect the environments of the planets inside them. 4.5 billion years ago, when our sun was young, it likely produced much stronger winds and a much larger protective bubble, similar to what we may be seeing in HD 61005 today. By comparing these new results with the direct data captured by Voyager at the boundary of the heliosphere, we can begin to trace the history of how our solar system became what it is today. This also brings us closer to understanding the conditions needed for life to emerge and survive in distant planetary systems. This is a very exciting step toward future discoveries.
Thank you for watching, and I'll see you in the next video. If you enjoyed this video, please don't forget to give it a thumbs up. Hit the subscribe button and the notification bell icon, so you'll be notified when new videos are released.